Okay, so we're now going to go on to the final part of the course. So just as a bit of a warm-up for you, you've seen a lot of skills in this chapter already and from year 12. So I'd encourage you to have a think about if you were given some velocity vectors, how would you deal with these kind of signals for what they wanted you to find in the question? So pause the video and here we go. So speed, we've talked about speed is a signal that we need to find magnitude. So Pythagoras is the way to do that. There are other clues. Sometimes you're asked, for example, about distance, maybe from the origin or the magnitude of the acceleration. Next, we have displacement from the start. So we need to integrate up for the displacement. And then depending on the exact question, substituting a value, something like that. Notice displacement would mean we're looking for a vector. Maximum speed. Now, maximum speed is an interesting one because earlier in this chapter, on one of them, we were told, I think it was something like this. Yeah, I think this was the equation. So this was an interesting one because you can use the range of something that you have in front of you. But one that you might be a bit more familiar with from year 1 is if you want the maximum of something, you can differentiate that thing and set it equal to 0. And that was a valid strategy that would have solved the question that we had earlier. It just would have taken a bit longer. So there's the maximum of something. It implies that, the acceleration is about to make it go the other way. If there's a maximum, it means something's going to get slower afterwards, for example. So that's another way you could have done that. Magnitude of acceleration we talked about as well. Distance traveled between 1 and 4 seconds. So that would be something where you would want to integrate. You'd want to use 4 and 1 as your limits. But you'd also have to be mindful that distance, like if you had a question where you were changing direction with your velocity, if you just do displacement, you sometimes end up in this situation where things cancel out. So you'd need to check you didn't have any turning points. So that one there, I would say, can be a relatively hard question because you've got to check and see what's going on. A very good strategy, if you've got a harder question and a bit of time, is actually to sketch the velocity time graph and you can spot these kind of things. And maximum acceleration, the same sort of thing I said about maximum speed. Just one more thing about maxima is if they say a maximum speed and maximum acceleration and they give you some time, you want to check the start and the end points of that journey as well. It might be that it started off at its quickest and then everywhere else in the journey was slower, for example. So start and end and turning points is a good way to do these ones here. Okay, so let's have a go at some questions, and I'm sure some of these ideas will come up along the way. So what's new in this part is this is more focused AT on integration. So we're expecting more integration here. So velocity is given by this. Velocity has t in it. Yeah, velocity t in it again. Now, just as an aside here, if I differentiated, can you see that the I has constant acceleration? So even though things have constant acceleration, we can still use calculus on them, okay? And if I differentiate this other bit here, what's that? That's just t, isn't it? Can you see that the j bit depends on t? So there's a constant acceleration bit and there's a variable acceleration bit here. So on these kind of questions, normally the best route is just to go down the variable acceleration route altogether, okay? But I'm afraid it's not as easy as, oh, it has i's and j's, so I should just differentiate or integrate. It's not always the best way to do it, or even the correct way. So that's the velocity. The position vector with respect to p is, what's this? Oh, so these two things go together, don't they? At time equals 0, the position vector, the displacement, if you like, is this. So this is going to be to help me when I integrate. So what I'm going to do is I'm going to integrate 3t and half t squared, because if I integrate that, that will give me my displacement. Okay, so I'm going to integrate them and just make sure I've got my notes in front of me. So when I integrate that one there, I get 3 over 2 t squared, and then the other one is a 6th t cubed. So this is a general expression for the displacement. But we've integrated, so we need a plus c, right? Now, because we've got I and j, what we actually sort of need to do is we need to do something like this. So for plus c, we're looking for a plus c for the i's and a plus c for the j's, and they don't have to be the same number. So I'm going to sub in this t equals 0, and I'm going to sub this in because these pieces of information go together, and it's the position vector, which is about the displacement. Okay, that's another way of saying displacement, really, from the origin. So if we sub these in, that's saying to me, isn't it? It's saying 2 minus 3 should be equal to 3 over 2, with the 0 in there. Okay, so that's kind of the first equation, if you like. And then the other one is saying, it's 0 in both of them. So you've got this idea again that there are lots of zeros, and actually, those numbers are just the c values. So you'll see a lot of that, but that would be sort of the formal way of doing it. Okay, and sometimes they don't give you t equals 0. So personally, I think it's not the worst idea in the world to substitute these in and find these out. So what is the position vector in general then? Well, we're going to just write this again with our c values, and we have found out that they are our c values. So it's that one, and it's minus 3, and it's that one there. Okay, it didn't say write it in I and j form, so I'm just going to leave it as a column vector. So that's it for the very first one. Let's have a go at a couple more questions. A particle is moving at time t seconds. Its acceleration. Okay, so I've got an acceleration. When t equals 3, the velocity is this. Okay, that looks like it's the thing to help me find the c. And then there's even more. And its position vector is this. Right. That sounds to me like that 3 is being reused a couple of times. So watch out for that. That's a little bit harder to spot. But I think we're going to need to use that 3 a couple of times. So what do we need to do? The angle, motion. Motion is about velocity. So the angle between the thing and I, so, for example, something like that, when t is 2. Okay, so the acceleration is 4 minus 2t. And we're going to start by finding that, which is going to be integrating that. So that is going to be integrating 4 minus 2t. So our velocity is going to be 4t minus t squared, and I'm going to just sort of put the c's in like that straight away this time. Our information was that green one, wasn't it? So the velocity is 6, 0. If there's no j, it means there's a 0. So 6, 0 should be equal to that when you make the t a 3. Okay, so a little bit like this. And if you do that, it looks like C1 is minus 6, yeah, which is what I have there, and minus 9, so that needs to balance out, so that must be a 9. So the velocity in general is 4t minus 6 and minus t squared plus 9. Okay, so that's the useful one. And now if I make t equal to 2, if I use t is equal to 2, I'm going to get an 8 minus 6, which is a 2. And then I'm going to get a minus 4 plus a 9, which is a 5. So if you draw that, it looks like 2 to the right, 5 up. And that's the angle that we're interested in, actually. So we'll write theta there. So inverse tan of 5 over 2 equals 68.2 degrees, which is what it looks like on my sketch. So I'm happy with that bit there. Okay, and notice we didn't use the red bit yet, so we're probably going to use that in the next part. What's the distance of P from O? And that's going to be when T equals 0. Okay, so I need to integrate this one here, don't I? So let's do that. So if I integrate V with respect to time, I'm going to get, where did I do it before? Okay, so I'm going to get the displacement equals what? 2t squared minus 6t, and let's put C1 there. And on this one, I'm going to get minus a third t cubed plus 9t plus C2. And we had some more information to help us work out the C values. So 3 goes with 20 and 3. So 3 goes with 20 and 3. So let's write 20 and 3 is equal to, okay, and I think hopefully you get the idea by now about what we're doing. Minus a third, 3 cubed, plus 9 lots of 3, plus C2. In the interest of time, I'm going to just give you those values. So C1 ends up being 20, and C2 ends up being minus 15. And you can save a little bit of time here because it says the distance. So for the distance bit, means we need to do the magnitude, yeah? T equals 0, well, we just noticed that, where is it? If you make the t bits equal to 0, you're only left with the C1 and the C2. So just find the magnitude of the C1 and the C2 bits. So you can just take these ones here and just do this. And it just wants the magnitude, which is 25 meters, because it's a distance. Okay, so that's all you need to do for that part B. And it's kind of just carefully reading it, working out what information is to maybe help you with the integration later. There's a lot of different things here. There's angle with I going on. There's the use of the word distance. But yeah, that sort of approach should help you with it. So that's it for your work examples. And then in the next video, we'll just do some of the test your understandings.